Okay, let's unpack this. There was this prediction recently from former Google CEO Eric Schmidt that really grabbed my attention.
Oh, yeah. What was that?
He said AI, maybe not too far down the line, might need the power equivalent of 90 nuclear plants.
90. Wow.
90, yeah. I mean,
Yeah.
that immediately flags a huge, like, looming energy crunch, right?
Yeah.
All driven by AI just growing and growing.
It's a pretty stark figure, and it really underlines the immense energy appetite these advanced AI systems have.
Absolutely.
Like, think about just the sheer computing power needed, training these huge models, running simulations.
It's massive. And our current energy setup, well, it might struggle to keep up with that kind of, like, exponential jump.
That's the concern.
Exactly. So you look at our usual sources, fossil fuels obviously have issues. Even renewables, solar, wind, they have limitations, intermittency, land use.
Right. Scaling them up that fast is a huge challenge.
So the big question, and this is really for you, the listener who wants to get up to speed quickly,
Okay.
is where is all this AI energy going to come from?
That's the core of it.
Yeah, and that's our mission for this deep dive. We're kind of zeroing in on this really fascinating, maybe unexpected link between the race for AI dominance and a very specific energy source, fusion.
Fusion. Yeah. The sun's power source.
Exactly. So consider this your shortcut to understanding what could be a really world-altering dynamic.
And it fits into this broader story, doesn't it? Humanity sort of climb up the energy ladder.
Energy ladder, I like that.
Yeah. From wood, coal, oil.
Yeah.
Always looking for more powerful, more efficient sources. And the material we looked at positions was fusion as, well, maybe the ultimate step.
Replicating the sun right here.
Pretty much.
The article even talks about this idea of, like, bypassing intermediaries.
What does that mean exactly?
Well, instead of digging stuff up or relying on the wind blowing, fusion could potentially give us direct access to almost limitless power.
Okay, right. Clean slate energy, potentially.
Yeah. And here's where it gets really interesting. The article talks about this global competition heating up. Because once fusion is cracked, once it works.
It could be copy-pastable. Is that the term they used?
That's the term, copy-pastable. Imagine no more drilling, no pipelines, crisscrossing the globe for fuel.
That would change everything. The geopolitics, the economics.
Totally. And speaking of competition, the article points pretty clearly towards China making some serious progress.
They have been hitting milestones, yeah.
Yeah.
Sustaining that fusion reaction for longer periods.
Right. What was it, like 101 seconds back in 2017?
And then a big jump, supposedly 1,066 seconds targeted for 2025.
Yeah.
Holding that super hot plasma stable for longer is key.
Definitely. That shows real progress towards actually generating power continuously.
And the article mentions their big goal, a fully operational net gain tokamak.
Net gain meaning more energy out than you put in to start it.
Exactly. That's the magic threshold. And they're apparently aiming for 2027.
2027, that feels incredibly soon for something like fusion.
It's ambitious, no doubt.
Yep.
If they hit it, that's a massive game changer.
But, okay, the U.S. isn't just sitting back, right? The article brings up CFS, Commonwealth Fusion Systems.
Right, the MIT spinoff, they're taking a slightly different tack.
How so?
Their focus is on smaller, maybe cheaper reactors, and the key seems to be these advanced superconducting magnets.
Ah, the magnets, crucial for containing the reaction.
Exactly. They're using yttrium-based ones, high-temperature superconductors.
Yttrium-based, okay.
These can create much stronger magnetic fields, basically letting you build a more compact, tighter containment vessel, a smaller tokamak.
Which could mean potentially faster development, lower costs.
That seems to be the hope, yes. A different path to the same goal.
Okay, so we've got China pushing hard on one path, the U.S. exploring another with these advanced magnets. But then the article throws in a curveball.
Ah, yes, the joker in the deck.
The joker, critical materials.
Right. It's not just about the physics and engineering, which are mind-bogglingly hard anyway. It's also about the stuff you need to build these things.
And the article highlights two specific ones.
Niobium and yttrium.
Okay, let's take niobium first. That's important for China's approach.
Yes, for the low-temperature superconducting magnets they're using. It's a key ingredient.
And the supply chain for niobium.
Well, according to the article, it's heavily dominated by China. They control over 90% of the supply. The actual ore comes mainly from Brazil and Canada, but the processing, the control...
Is largely in China.
Yeah.
Okay, that's significant.
Very.
Now, what about yttrium? That's the one the U.S. needs for their high-performance magnets.
Yes, crucial for the CFS approach, these smaller, high-field tokamaks.
And the situation there?
Similar story, unfortunately. The article states China has a near monopoly on refining and producing yttrium.
So wait, even if the U.S. tech works perfectly?
They could still depend on China for a absolutely vital component to actually build the reactors at scale.
Wow. Okay. That adds a whole other layer to this. It's not just science.
Not at all. It highlights a potential supply chain vulnerability, right? A bottleneck.
It really does. The implication is stark. Perfecting the tech isn't enough if you can't get the materials.
And connecting that dot to geopolitics.
Huh?
Well, the control of these rare earth elements, as the article suggests, becomes a major strategic lever.
A lever for maneuvering. The article even hints at connections between U.S. interest in places like Greenland or Ukraine and their potential rare earth reserves.
It draws that line, yeah, suggesting that access to niobium and yttrium might be part of the strategic calculation in those regions,
So the equation it lays out is basically rare earth control equals energy sovereignty.
which in this future scenario could equal AI supremacy.
That's a powerful chain of logic.
There's a quote in the article that sums it up well, something like,
Oh, the poker game one.
yeah, this is a poker game where everyone bluffs,
Yeah.
but the goal is the same.
Yeah.
Energy to power AI.
That really frames it, doesn't it? High stakes.
Definitely.
And then there's another twist, this idea of the AI flywheel.
Right. This is where it gets even more interconnected.
Explain that simply. AI helping to make better AI.
Sort of. The idea is that as AI gets more powerful, it can accelerate breakthroughs in other fields, including material science.
Ah, so better AI could help us discover better materials.
So for things like fusion reactors,
Mm.
potentially. More efficient superconductors, perhaps,
Which then provides more energy.
to power even more advanced AI. It's a self-reinforcing loop.
A positive feedback cycle. AI driving energy breakthroughs, which drives better AI.
Exactly. And the article suggests this flywheel could spin much faster than, say, the development cycles we saw with early computers. The impact could be quicker, more profound.
Faster acceleration. Okay, and you mentioned superconductors. That seems key.
Absolutely fundamental to the magnetic confinement in tokamaks. But there's a mystery there, too.
What's the mystery?
Well, the article points out that, honestly, scientists still don't fully understand why some materials become superconducting at certain temperatures.
Really? Even after all this time?
Their fundamental mechanism isn't completely pinned down. So finding new superconductors is often, well, a bit of trial and error.
Mixing things together and seeing what happens.
Largely, yes. Testing countless combinations, which is slow and painstaking.
But that sounds like something AI could be good at.
Precisely. That's the hope outlined in the article. AI could simulate and predict material properties, sifting through possibilities vastly faster than human experimentation.
Searching for better superconductors, or maybe even the Holy Grail.
Room temperature superconductors.
Imagine that. No need for extreme cooling.
It would be utterly transformative. Fusion could become a much simpler, maybe even smaller scale technology. It changes the entire engineering challenge.
Okay, that's a huge potential upside. But the article does offer a bit of a counterpoint, right? A sort of reality check.
It does, yeah. It raises the question, what if this assumption of exponential AI energy demand is wrong?
Meaning, what if AI gets way more efficient?
Exactly. There's a lot of work happening on AI energy efficiency. Techniques like model distillation, making smaller, leaner AIs that do the same job. Or mixture of experts, where only parts of the AI brain activate when needed. Kind of like how our own brains work to save energy.
So AI might just get frugal enough that we don't need 90 nuclear plants worth of extra power.
It's a possibility. The demand might level off or grow much more slowly than those dramatic predictions suggest.
But interestingly, the article says even if that happens.
Right. Even if the massive demand spike doesn't fully materialize, the arrival of potentially cheap, abundant energy from this AI fusion flywheel, well, that alone would still be revolutionary.
Yeah, the impact of near limitless clean energy, regardless of AI's specific needs, would just ripple through everything.
Global economics, industry, geopolitics.
Yeah.
Everything changes if the energy foundation shifts that dramatically.
So, wrapping this up for you, the listener, the article really boils it down to a powerful conclusion.
Yeah, the final takeaway is pretty stark.
Whoever solves the energy problem wins the AI race. And whoever wins the AI race reshapes the world order.
That puts it bluntly. It frames the fusion race not just as science, but as a direct competition for future global leadership.
Absolutely. And these seemingly minor materials, niobium and yttrium,
They turn out to be these unexpected, critical jokers in this incredibly high-stakes game.
it really shows how dependent these futuristic technologies still are on basic resources and who controls them.
A powerful reminder of those hidden dependencies.
So maybe the final thought to leave you with is this. Forget just the tech for a second. What actually happens to our world, our societies, our global structures, if energy, this fundamental building block, effectively becomes almost free, almost unlimited?
It's a question with implications far beyond just faster computing. Something to really chew on.